SCHEMCON 2022, sponsored by Viatris and powered by SVL Engineering Services Private Limited, Chennai, Indian Oil, Saraka Laboratories Limited. As part of this SCHEMCON 2022, we are having online lecture series. So earlier we have seen Dr. Abhijit Majumdar from IIT Bombay delivering his lecture, Dr. M. Nabil, IIT Tirupati delivering his lecture online, and Professor Selvaraj, IIT Guwahati delivering his lecture online. And we also had M. Mishra from Nuclear Fuel Cell Complex, Hyderabad delivering his lecture online. Now we are going to have Engineer Mr. Baskar, Process Engineer at SAIPEM Sharjah, UAE, who has accepted our invitation to deliver his online talk within short notice. We thank him on behalf of Department of Chemical Engineering, National Institute of Technology, Warangal, and IICHE, Hyderabad Regional Center. We thank him and welcome him to deliver his talk. Over to you, sir.
Column design during design stage itself, because once the column is built and the process is fixed, then it will be very difficult to make many changes in order to optimize the design. So it is very important in the design stage itself we make proper optimization and proceed for the design. I will go through the presentation. If anybody have any questions, definitely you can stop me in between and you can ask. I will be glad to answer you. In today's presentation, we will be covering the small introduction to distillation and why energy saving is important in the distillation process, and what are the key parameters that can be used to optimize the design. And we will see the key parameters one by one and how it will impact the design and the optimization. Introduction to distillation. Many of us know what is the distillation process. Maybe few people may not aware of it, so I will just touch upon brief description for the distillation. Basically, distillation process is the core of a process unit which converts the multi-component feed into desirable products. You can take any petrochemical product which is in the market now. Definitely all this product would have been come through the distillation process only. So you can imagine how much the distillation process is very important in the process design, because almost all the refinery, all the petrochemical plant, they will have definitely the distillation process in order to make the desirable product. And the principle behind the distillation is the difference in the boiling point of the components. Since the multiple feed components, each component will have different boiling point, the distillation process is based on the different boiling point, the components will be split into the desirable product. And this can be achieved by the repeated evaporation and condensation of the mixture, which can allow the complete separation of the components. I hope everybody understand by distillation. I hope already you might have studied in the academics, right? Or I can little bit explain on that one. This is the typical configuration of the distillation column. The feed will be introduced into the distillation column. In most of the cases, the feed will be in two phases, that is vapor and liquid mixture, and the feed will contain multiple component mixtures which will have a boiling rate starting from low to high. So when the feed is introduced into the distillation column, the vapor will travel towards the top of the column and the liquid will travel towards the bottom of the column. The vapor, I hope you can see my mouse on the screen, right? Where I'm explaining. Hello.
Yes, sir, we can see.
Okay, fine. Right. Okay, the vapor traveling towards the top of the column, it will get in contact with the cold reflex from the top of the column, and this vapor will get into touch with this reflex, and since the reflex will be at a low temperature, it will condense the heavier boiling components in the vapor, and it will take that heavier components into the bottom of the column. The same way, whatever the liquid entered into the distillation column will travel towards the bottom of the column, but the vapor which is coming out from the reboiler will be at a higher temperature. This vapor at a higher temperature will boil up the lighter component. Lighter component means which will have the low boiling point, that will vaporize the lighter component in the liquid, and then it will take along with the vapor, and the light component will travel towards the top of the column where it will be condensed in the condenser. And the total vapor will be condensed, and the liquid will be sent to the cold, sent to back to the column as a cold reflux, and part of the liquid will be withdrawn as the top product. And in the reboiler, we will have it can be heated by either steam or hot oil depending on the heating medium available, and the bottom, whatever the liquid collected, it will be sent to the reboiler where it will get in touch with the steam, and it will be heated up, and it will be partly vaporized, and it will be sent back to the vapor, and the liquid whatever is there, it will be collected as the bottom product. I hope this is clear. Now, in this distillation column configuration, here the major energy consumers are the overhead condenser, because we need a lot of cooling medium, which is cooling water, or it can be a air cooler also. In most of the refineries, there will be a cooling water will be available as a cooling medium that will be utilized for the condenser, and in some cases, air cooler also will be used as the overhead condenser. Whether it is a cooling water or air cooler, anyway, to generate the cooling water also we need energy, and even for air coolers to drive the fans we need energy. The same way, in the reboiler, either steam will be used as a heating medium, or hot oil will be used as heating medium. Both to generate steam or hot oil also we need more energy. And another energy consumer in this distillation column is the reflux pump. Many of the columns will have a huge reflux rate in order to achieve the top product quality. Hence, the reflux pump also will require more energy. So there are many energy consumers in the distillation column, and we are going to see how to optimize the energy in the presentation. Okay, why energy saving is important in the distillation? As I said, there are simultaneous heat input and removal in the distillation process, because heat input is given in the reboiler and heat removal is being carried out in the condenser. Since both are simultaneously happening, there is a potential chances for optimizing the energy in the distillation column. In refining and petrochemical industries, almost 40% of the total energy is only utilized in the distillation column itself. So when we optimize the energy consumed in the distillation, we can able to decrease the total energy consumed in the overall plant itself. As I explained, the major energy consumers are the condenser, reboiler, and the reflux pumps. Now we will see what are the key parameters that can be changed or altered in order to achieve the optimization in the distillation columns. The key parameters are the column pressure, then feed temperature, number of stages, and the feed stage location are very important in the distillation column. Then the reflux rate and the pump rounds. We will see one by one how these parameters play a role and how it will affect the distillation process and how it can be optimized. So the first one is the column pressure optimization. Choosing the column pressure is very important in the design of the distillation column. Always the lower pressure typically saves energy, because you might be knowing for each component, when at low pressure the boiling point also will be very low. So it will be easy to vaporize in the reboiler. Hence we can definitely save more energy where if we keep the pressure very low. And also at low pressure, since the vaporization can be done easily, there will be more generation of vapor, and it will increase the mass transfer rate inside the distillation column, and hence better fraction also can be achieved. And apart from this one, this low pressure will help in reducing the capital cost of the column also, because the pressure rating of the column also will be less, and also the associated equipment also will be rated for the low pressure. So the column pressure helps in both ways. It will reduce the capital cost as well as the operating cost as well. If anybody have any doubt, please let me know. I'm going on, but I hope it's understandable or easy to. Okay. Now I have shown a simple chart which I have done for a case study in the debutylizer column, how the impact of reducing the pressure, how much the cost can be reduced. You can see from this graph, even 10 to 20 psi of reduction in the pressure, how much it saves, nearly around $100,000 of per year it is can be saved. This analysis we have done for a deep business column. Unfortunately, due to confidential information, I could not able to break down the each component cost for the each component, but I have given the overall energy cost saving in the debutylizer column. You can simply, this is to only to emphasize the fact that even 10 or 20 psi reduction also can help with a large energy savings and cost savings in the distillation column. However, this chart only it is applicable for this deep column and it cannot be used for the other applications, because each application the impact of pressure will be different depending on the whatever the feed composition we have. Okay, now we have known that the column pressure is very important and it should be kept as low as possible, but how to choose the right operating pressure? I will explain how the pressure has to be chosen because now I will go back to the configuration again in order to explain more. Okay, now we have the top product which is called the distillate, which is the low boiling component which is present in the feed, that has to be withdrawn from the distillation column as a top product. Now this product, let's say for example this top product is here naphtha or gasoline. This product will have its own boiling point at a pressure and temperature. Now in this condenser, for example, if it is we are using a cooling water as a cooling medium, the cooling water will be available at a temperature of 33 degree or 35 degree in the plant. We cannot have a cooling water less than that because our ambient temperature itself will be in that range and we cannot have a cooling water less than that one. So if cooling water is available 33, we can condense this vapor at slightly higher than this 33 degrees centigrade. For example, we can cool up to maximum of 38 to 40. So by somehow indirectly this condensing temperature will be getting fixed depending on the cooling medium whatever we are using. If you are using the air cooler, let's say if you are using an air cooler as a condenser, then the condensing temperature will be slightly more because the ambient air will be available at a more temperature in the summer. Hence, this condensing temperature will be dictated by the cooling medium whatever we are using the condenser, and it will be, let us say for example, if you are using the cooling water, it can be around 35 to 40 degrees Celsius. So at this temperature, in order to condense this top product, we should have a minimum pressure, otherwise it cannot be condensed. Because at a particular temperature, this product will have a minimum pressure at which this product can be condensed. Let's say for example, in this case, if this pressure is corresponding to the temperature of 45 degrees is 5 bar G, now we cannot decrease the reflection pressure less than 5 bar G because our intention is to condense the entire vapor into liquid. So accordingly, this 5 bar G pressure will be fixed now, and now we can back calculate the column pressure by allowing some delta P across the top piping and the condenser. Normally in the condenser it will have 0.5 to 0.7 bar pressure drop, and in the line it will be 0.1 maximum. So if it is 5, then it will be 5.5 here, and it can be accounting 0.1 bar in the pipe, it will be 5.6 bar G. So as a minimum, this column can have a minimum of 5.6 bar G pressure only. We cannot reduce further. So this is how the column pressure will be dictated by the top product. Now, once the top the pressure is fixed, then the bottom pressure will be fixed only by the pressure drop across the column. Normally, the pressure drop across the trays will be 7 to 10 mmHg per tray, and based on the total number of trays, we can account the total pressure drop across the column. That is how the bottom pressure will be fixed. So this will dictate the column pressure profile in the distillation column. That is what I have explained here. When choosing the operating pressure, first the reflux drum pressure will be fixed based on the condensing temperature at the top with the available cooling medium. As I explained, if it is cooling water, then we can have a maximum of 35 degrees Celsius as the condensing temperature, and we have to calculate what is the corresponding saturation pressure for the top product, and that will be dictate the reflux drum pressure. And the top stage pressure can be calculated from the reflux drum by accounting a pressure difference for the condenser. For vacuum columns, we cannot have more pressure drop, hence it will be in the range of 0.01 to 0.03 bar. For atmospheric columns, it will be around 0.5 to 0.7 bar. Then, as I said, the bottom stage pressure will be calculated by accounting the pressure drop across the trays. This is how the column pressure will be fixed during the design stage. So even though our intention is to keep the pressure as low as possible, but sometimes it will be dictated by what is the top product and what is the cooling medium available. In some cases, the operating pressure can be a constraint also. For example, even though the operating pressure should be low in order to optimize the energy and optimize the design, sometimes we cannot decrease the pressure because it depends on the overall hydraulic profile of the plant. For example, if the feed is coming, I will go back to this one. If the feed is coming at high pressure and the product also to be sent to a location where high pressure is required, then we cannot decrease the column pressure only for optimizing this distillation column, because again, if we decrease the pressure, again we have to pump it to a higher pressure. So that will not be economical. Hence, the column pressure will be also depend on the total hydraulic profile of the plant. If there is no constraint, for example, no, the product is not need to send for a very high pressure source or high pressure destination, then definitely we can reduce the column pressure. That is what I explained here. If the feed is coming from high pressure source and the products also to be sent to high pressure destination, then it will not be economical to reduce the column pressure. In that case, we have to fix the column pressure in line with the feed in order to allow the product to flow to the high pressure source or high pressure destination. And lowering the pressure will also result in the high vapor volumetric flow, because at low pressure, the vapor, whatever inside the distillation column, will have lower density. We know rho equal to Pm by RT. So when P is low, rho also will be low. So if density is lesser, it will have a higher volumetric flow. Since higher volumetric flow is there inside the column, it will require a large diameter. Otherwise, there may be chances of flooding in the column. This will result in the higher size of the column. But if we compare the potential saving in the energy, this will not be a big impact, because this higher size of the column is going to be only one-time investment, and anyway the operating cost will be a continuous saving in the operating cost. And another thing what we have to check during selection of the operating pressure is we have to check the water dew point also. When we are lowering the operating pressure of the column, there is more chance that the water which is present in the feed, in most of the cases the water vapor also will be there. At lower pressure, the partial pressure of water also will be less, and it will try to condense in the top of the column. If free water is present in the inside the column, then it will lead to a corrosion problems. So in order to avoid the condensation of water inside the column, we should check the water dew point at the top pressure, and accordingly we have to adjust the top pressure so that the water is not condensing and there is no free water formation. If the water is present in the form of vapor, then there is no issue. Only if the water is condensing and it forms a free water phase, then only the corrosion problem will start. So this is how the operating pressure of the column will be fixed, and these are the checkpoints while selecting the operating pressure. Now we'll move on to the next one. The next parameter is the feed temperature optimization. Hotter feed can increase the feed vaporization. As I told, if the feed is itself is having two phases, and if it is coming with the increased feed vaporization, then the reboiler duty will be decreased. Because the reboiler purpose itself is to generate more vapor in order to provide a more vapor liquid contact inside the column. If the feed itself is having more vapor, then reboiler duty can be reduced a lot. And this can be achieved even by exchanging the heat with the bottom product coming from the reboiler. Anyway, the bottom product which is coming from the distillation column will be at a higher temperature that can be used to preheat the feed which is entering the column. And what will be the optimum feed temperature? It is good to have a feed temperature which is closer or above the boiling point of the feed. I can simply explain how it can be done. So in the previous configuration, we have seen the feed is directly, sorry. In the previous configuration, we have seen the feed is directly entering into the column. But in this case, you can see the feed is first going to an exchanger where it is being heated by the bottom product which is coming from the reboiler. Always the bottom product will be at higher temperature because in the reboiler we are providing energy to heat the bottom liquid coming from the column, and we are vaporizing it, and thus heat can be utilized to preheat the feed which is entering into the column. So by doing this one, we can reduce the heat duty required for the reboiler. This is one of the optimization that can be done during the design stage. And another variable is the number of stages and the feed stage location. This is very important because the number of stages and the feed stage location plays a very predominant role in the optimization of the energy consumers. We all know that the number of stages and the reflex rates are interlinked. When there is a more number of stages, it will require less reflex rate. And that means reflex rate means it will reduce the condenser duty and also the reflex pump duty. In a way, it will help in reducing the reboiler duty as well. And also the stages at which the feed entering the column. The feed can enter at any stage of the column, but the location where it enters also have a strong impact on the duty of the column. When the feed stage is too high, for example, when the feed stage is entering very much near to the top of the column, then high reflex rate is required to meet the top product specification, because the composition entering into the feed which will not be equivalent to the top product what we are going to get it from the column, and hence high reflex rate is required in order to meet the top product specification. The same way, when the feed stage is too low, more reboiler duty is required to meet the bottom product specification. Now, how to optimize this number of stages and feed stage location, that I will explain through a example. We will take the typical example of the LPG stabilizer. This is LPG stabilizer, and the feed is coming from the deethanizer from the upstream. And from here, we have to separate out the LPG, which is predominantly the C3 and C4s, and we have to reduce the C5 in the LPG. And the specification required is the C5 in the LPG should be less than 0.1 mole %. And the bottom product should be the gasoline, and it should have a RVP of less than 50 kPa. These are the constraints provided for us in a refinery plant, and according to this LPG stabilizer has to be designed. In this column or in this typical example, I will tell you how we have optimized the number of stages and the feed stage location. First, what we will do, this fixing this number of stages and feed stage location is a little bit trial and error process. First, we will fix the number of stages in the bottom. Let's say in this case, we have fixed the number of stages in the bottom as 5, and we increase the number of stages by 2, 16, 18, 20, and 22. And then we have observed that whether how much is the reflex rate required in order to meet our specification. You can see in all cases we have met the specification required. In the top product, C5 percentage is less than 1%, 0.1 mole %, and the gasoline RVP is less than 50 kPa. And you can see in order to achieve this product specification, how much the reflex rate is varying. If you take the 60 number of stages, it requires 380 kiloliter per hour. And if you increase the number of stages, and the reflex rate is coming down. Now, the next step what we have done is, now we increase the number of stages in the bottom as 8. Then we repeated the analysis by increasing the number of stages in the top. You can see the bottom stage we kept 8 for all the trials, and we increase the number of stages in the top. And now, in order to meet the same specification, we observe what is the reflex rates. We have noted down what are the reflex rates that are required in order to meet our product objectives or specifications. The same way, the number of stages in the bottom in the next step we increase from 8 to 11, and we repeated for the number of stages from 16 to 22. And we have observed, or we noted down the stabilizer reflex rate in order to meet the product specification, how the reflex rate is changing. Now, if you plot this data in the curve, you can simply see how much difference it makes, the number of stages and the feed stage location. Now, this is the number of stages in the top, which varies from 16 to 22, and this is the reflex rate. You can simply see that when the number of stages increasing, then the reflex rate is reducing a lot. The same way, when you are increasing the bottom stage, that means from going from bottom stage 5 to 8, the reflex rate required also is jumping from very high to, let's say for example here around 400 to it comes to 170. There is a drastic reduction. And from increasing from bottom stage to from 8 to 11, again the reflex rate has come down. But you can see from the decrease of the net quantity decrease from bottom stage 5 to 8 is not the same when we jump from 8 to 11, because almost it is coming to a saturation level. Now further, if you increase from 11 to 13 or something also, the net difference between the change in the reflex rate will be very small. The same way, if you see in the number of stages in the top also, from when you increase from 16 to 18, the difference is large, but when it goes from 18 to 20, it is the difference is coming lesser, and again it is coming negligible. This is how we can see that there is a saturation coming over with respect to the number of stages. Now from this one we can pick up where we can optimize the reflex rate. For example, if we choose any point here, that will be the minimum optimum rate for the reflex, and accordingly we can choose the number of stages as from the top it is 22 and in the bottom as 11. And if we have or if you want to analyze further, we can increase another step with the bottom stage as 13, and then we can do the analysis also. But we have stopped because we could see that there is no big saving, and hence we stopped here. This is how we will fix the number of stages during decision stage in order to optimize the reflex rate. As I said, if we optimize the reflex rate, there we can optimize the condenser duty, reboiler duty, and as well as the reflex pump duty. That is the reason I said optimizing the number of stages is very important in the distillation column, since it can impact all the duties or all the energy consumers which are required for the distillation process. This is very important. I hope it's clear for all. If you have any doubt, please let me know. Okay, now I'll go to the next one. Reflex rate. Now, as I said, the reflex rate also can be further optimized once you select the number of stages, the total number of stages, and the feed stage location. We can do a sensitivity analysis by meeting the product specification, and by compromising the product specification, how much is the reflex rate changes. But our objective is to, if it is we cannot compromise on the product quality, then we have to meet the whatever the reflex rate required, or if our objective can be slightly compromised, or the product specification can be slightly compromised, we can see how much it can give a savings in the reflex rate. Now you can see if our C5 in top product can be allowed from 0.1 to 0.15, how much there will be a decrease in the reflex rate. It will be from here to here. But in our case, the client or company did not allow us to compromise, and hence we have selected the reflux rate which will meet the required product quality. But in some cases, we can explain to our company or client saying that if we slightly compromise on the product quality, there can be potential of large saving. So to this sensitivity analysis, we have to do the reflex rate with respect to the product quality by fixing the number of stages. Once we generate this kind of graph, it is also a trial and error process. Once we do this graph, once we generate this graph, from here we can simply know how much the reflex rate is very sensitive with respect to the product qualities, and it will allow us to choose a optimum reflex rate. Now the next one is the pump arounds. Pump arounds is not a variable, but this is one of a method, we can say. This is one of a method which can be used to optimize the energy savings in a column. Pump arounds are used to remove the excess heat from the column, and increasing the pump around rate will reduce the reflex rate required at the top. First, I will explain what is the pump around. You can see this is in between a column. There will be a pool of liquid which will be withdrawn from the column, and then it will be cooled down, and then it can be returned to the column. Because once the required amount of evaporation is done, then there will be more excessive heat energy available within the column, which will again go to the vapor at the top vapor, and we have to condense it again. Instead of doing that one, we can withdraw from the middle of the column itself, and it can be cooled and then returned back to the column. But this cooling can be also achieved by utilizing this heat by preheating the feed itself. That is how these pump arounds will be useful in the energy optimization. Yeah. Increasing the pump around rate will also reduce the reflux rate required at the top, and also it will decrease the condensing duty also. As I said, the heat required from the pump arounds can be used to preheat the feed entering the column, so the feed temperature also can be optimized. Normally, these pump arounds are used in the crude fraction towers because there will be loss of excessive heat which will be in the crude fractionation towers, and these pump arounds, even not only one, there will be multiple pump arounds in the crude fractionation towers in order to utilize this heat available in the distillation column. This is also one of the optimization method which can be considered for the distillation column. Yes, that's it. We have seen the key parameters and also another method which can be used for the distillation column. Thank you for your time. If you have any questions, please shoot me.
Thank you, sir. Participants, if there is any queries, you can let the speaker know so that he will be responding to this. Sir, I was wondering, you were mentioning about this pump arounds.
Yeah.
So if we put multiple pump arounds,
Yes.
not only in a single stage, will
Yes.
that be also be beneficial?
Yes. Normally, crude fraction towers will have 2 to 3 pump arounds. Here, for simplification, I have just shown only one example.
Okay. And how about the position? Where
Position, we have to choose. Actually, we have to choose the position based on the product what we are withdrawing. It is not a straightforward. It has to be it also be in conjunction. We have to see the product what we are withdrawing.
Okay. Yes. Participants, any other questions? Okay, that I think no further queries, sir. So thank you so much for your time and as well as efforts, sir. So we highly appreciate your contribution to our conference, sir. Thank you so much, sir.
Thank you.
Winner, bro. Chicken dinner, bro. Dancer, bro. Ekdam killer, bro. Bro, ni chandi life